section 6.6, we're going to talk about the periodic table and ions. All right, so what is an ion? Well, an ion is an atom with a charge due to either losing or gaining an electron. All right, if you guys remember, an electron has a negative charge. All right, so if an atom gains an electron, like it would in some sort of chemical reaction maybe, then it would have a negative charge. If an atom loses an electron, then it would have a positive charge. Some examples of some ions right here, this is how they're written. So this one is potassium. The first one is K, potassium, and it has a charge of +1, so there's just a positive ion there. Right, and next one is iron, Fe, has a +3, oxygen -2, and chlorine negative, and it's actually, this is a -1. So you don't have to write the 1, but if chlorine gains an electron, it would have a -1 charge. Now, if it's a positive ion, if it's positive, it's going to be called a cation. If it's negative, it's called an anion. So our positive ions, our cations here are the potassium, the iron, and that's it. Our negative ions, our anions, are oxygen and chlorine. All right, and I always remember that the anion is the negative because there's an N here, anion, and negative starts with an N. Valence electrons are the number of electrons in the highest energy shell. So if you guys remember back to our electron configurations and orbitals, it's going to be the number of electrons in the highest shell going from 1 to 8. All right. If you guys remember, the noble gases right here that have a total of 8 electrons in their outer shell. This means that they have the ending configuration of S2p6, right? And that's 8 electrons in the very outer highest energy shell. If we look at this, if you guys remember that first row, they all end in S1, second row, S2. This one is going to be S2p1, so there's 3 in that one. So these are the number of valence electrons that we can predict are going to be in the outer shell for each element. There's 1 in group 1, 2 in group 2, 3, 4, 5, 6, 7, and then lastly 8 for the noble gases. We are not going to talk about the transitional metals right now. We're going to skip over them. We're just talking about the S and P. So the noble gases have 8 electrons in their outer shell, and they're inert. They don't like to react with other elements, and this is because of the octet rule. It's described in the octet rule. So the octet rule states that electrons want to fill their outer orbitals to match a noble gas. So all elements like to have a full shell of electrons in their outer shell. Like if they don't have 8 electrons, they will either lose or gain electrons to get there. All right, so let's go ahead and do some examples. So the first one is sodium. So sodium is right here in group 1. If you guys remember, it has an electron configuration. Let's go ahead and write it. 1s2, 2s2, 2p6, 3s1. All right, so it has 1 electron in its outer shell. Remember, here's our valence electrons. 1, 2, I'll go ahead and write those. 3, 4, 5, 6, 7, 8. Okay. So how many valence electrons does sodium has? It just has 1. Now, would it be more likely to lose 1 electron or gain 7 electrons to have 8 in its outer shell? Well, it's going to be more likely to lose 1 electron. Now, if you lose an electron, remember each electron has a -1 charge, so it's actually going to have a positive charge because it just lost 1. So it would have it would be like this was gone, the 3s1. So then it would have a full outer shell here with a 2s2, 2p6. And it has just lost an electron, so it has a +1 charge. All right, let's go ahead and look at fluorine. So fluorine is over here when the halogens in group 17. So how many valence electrons does fluorine have? Well, it has 7. All right, now it wants to have 8. Wants to have 8 in its outer shell. It wants to have 8 valence electrons. So is it more likely to gain 1 electron or to lose the 7? Well, it's going to be more likely to gain an electron. And since each electron has a -1 charge, the charge on the fluorine will be a -1 charge. Okay, and that's going to be true for all, remember, like groups share similar properties, so every element in this group is going to be more likely to gain an electron, and they will have a -1 charge. So let's go ahead and look at this in more detail. So we remember sodium, we said, has a +1 charge. Fluorine has a -1 charge. All right, now let's look at something kind of in between. So let's go ahead and look at boron right here. Okay, so boron right there has, so the valence electrons are 1, 2, 3. So it has 3, boron has 3 valence electrons. Right, now how many, I spelled that wrong, valence, there we go. So would it be more likely to gain 4 electrons or to lose 3? Well, 3 is less than 4, so it's more likely to lose 3 electrons. Now, if you lose 3 electrons, that means you're going to have a +3 charge, because they're opposite. If you lose the electrons, then it's going to be positive. If you gain electrons, it's going to be negative. So the boron actually has a +3 charge. Okay, and it's going to be the same here. So in group 2 over here, if we look at barium, barium has 2 valence electrons. It's going to be more likely to lose the 2, so it's going to have a +2 charge, and that's going to be the same for every element in that group. Magnesium, calcium, strontium, all those going down will have a +2 charge when they make an ion. Now let's look over here at oxygen. So oxygen has 6 valence electrons, so it wants to get to 8, so it's going to gain 2. When it gains 2, it's then going to have a -2 charge. When it gains 2, it's going to have a -2 charge. All right, nitrogen has 5 valence electrons, so it's going to gain 3, so it'll have a -3 charge. And that's going to be the same for phosphorus, for arsenic, for antimony, all the way down. Now let's go ahead and look at carbon. Now carbon has 4 valence electrons, right? That's right in the middle. And actually what happens is that it really doesn't form ions very easily, so we're not going to consider it. We're just going to like kind of scratch this group out. But the rest of these, and we know that noble gases, they're not going to gain or lose electrons because they're happy. They just want to stay where they are, right? But these are going to be the charges for each of the other groups. So for fluorine, chlorine, bromine, it'll be -1. Oxygen, sulfur, selenium, -2, going all the way down, okay? So this gives us an idea of saying where, depending on where the element is on the periodic table, we can predict what's going to be the charge of the ion. Now you might notice that most of the metals here, over here, all are positive. So the metals are positive. And remember, those are called cations, right? The nonmetals on the right there, the blue, the nonmetals are negative. And those are going to be remember, those are the anions. Anions are negative. All right, so let's talk about those transitional metals. So the transitional metals, if you guys remember for electron configuration, the trend for the transitional metals is that they all end in the D group. Now the D group is a really big, or D orbital. The D orbital is a really big shell, and it's hard to predict what kind of charge transitional metals will have, and they can have multiple charges just depending on how they're processed and the environment they're in. So you can't really predict the charge on a transitional metal. So what we do is you're told. All right, so the Roman numeral, they use Roman numerals to tell you the charge. So if you remember Roman numerals, capital I equals 1, 2 I's equals 2, 3 equals 3, and then I and a V equals 4. And that's pretty much as many as you'll get. Well, I guess maybe V will equal 5. All right, so this is Roman numerals right here, right? Those tell you the number. So the way it's written is they'll write the element symbol, like for manganese, it's Mn right here, and a 2, All right, so this tells you that you have an ion that's manganese, and it's going to be positive because it's a metal, positive 2. So they're all going to be cations. If we have manganese with Roman numeral 3 after it, it's going to be manganese positive 3. So the charge of the transitional metal is always positive, and it's given to you by the Roman numeral in parentheses after it.